the last video, we have discussed about how to make an extrinsic semiconductor from an intrinsic semiconductor. That is done by adding impurities. So let us discuss in depth about extrinsic semiconductor by considering simple example. So let us consider that we have a silicon block and we added impurities to it. To make it as an extrinsic semiconductor block. So let me write. So this is pure silicon and this is silicon with impurities. Now let us say the impurities are aluminum atoms. Okay, so we have added a third group element as an impurity. So automatically this final silicon block with impurities is a p-type semiconductor. Okay, now for example, if I consider that the original silicon block has Ni number of carriers, which it means that the number of electrons in the in the conduction band and the number of holes in the valence band all are equal to Ni. Okay, all are equal to Ni. Okay, each of them is equal to Ni. Okay, now so here just because we are going to use Ne and NH even in the extrinsic semiconductor, let me call these as Ne0 and H0. So Ne0 and NH0 are the number of electrons and number of holes in the intrinsic semiconductor, that is pure silicon. Now let us say we have added NaL number of aluminum atoms per every unit volume. So Ni is, we can say, is the number of intrinsic carriers in the pure silicon per unit volume, and NaL is number of aluminum added per unit volume. And now let us discuss about the number of holes and electrons in the silicon with impurities, that is extrinsic semiconductor. So please follow this carefully. Now what happens is, since I said we'll take an example, as an example let us consider that in the intrinsic semiconductor there are 10 to the power of 11 per unit volume. So the number of intrinsic carriers per unit volume, let us say it is equal to 10 to the power of 11. Okay, and typically there are some 10 to the power of 23, around that many silicon atoms per unit volume. Okay, and as we discussed in the last video, maybe we have 1 in a million silicon atoms is replaced by aluminum atom. So if there are 10 power 23 silicon atoms and every 10 power 6 silicon atoms we have one aluminum atom, even then per unit volume the number of aluminum atoms will become 10 to the power of 17. It's a very simple calculation because you have 10 to the power of 23 silicon atoms, and out of which for every 10 power 6 silicon atoms, we have added one aluminum. So number of aluminum is nothing but number of silicon per unit volume divided by 10 to the power of 6, which is around 10 to the power of 17. Again, I am telling you, this is not always true. This is just an example that I am giving. Okay. Now, please try to understand that although we have added only one aluminum for every 10 power 6 silicon atoms, okay, in comparison to the holes and electrons that were already present, the number of aluminum atoms are actually a lot. I mean, they are around 1 million times the number of holes or electrons present. Okay. So always please understand, number of silicon atoms are 10 power 23 in our example, and it is close to reality also, 10 power 23. Now, mostly the covalent bonds will be formed only at some very rare places. The whole electron pair gets generated in the intrinsic semiconductor, and therefore for 10 power 23 silicon atoms, you have only 10 to the power of 11 holes or electrons. Okay. Now, for every 10 power, I mean, while you have 10 power 23 silicon atoms, we have made 10 power 17 aluminum atoms as impurities. That means for every 10 power 6 silicon atom, there is only one aluminum. Okay. But the density of electrons and holes in the intrinsic semiconductor is even lower. Okay. So while the silicon density is 10 power 23, aluminum density is 10 power 17, the original hole and electron density is much lower at 10 power 11. Now, please understand. Okay, silicon is the base. And as you know, since aluminum has only 3 electrons in its valence shell, every aluminum adds a hole without adding electron. Without adding electron. So, if you consider any unit volume, there were 10 to the power of 11, which translates to around 10,000 crores. Okay. So you have 10,000 crores, okay, of electrons or holes every unit volume in the block, in the intrinsic semiconductor. Now, in that unit volume, every unit volume, we have added 10 to the power of 17 aluminum atoms, and every aluminum atom causes a hole. Because of this, you have 10 crore, okay, holes generated every unit volume. Now you see 10,000 crore and 10 crore. When you add 10 crore to 10,000 crore, it's a simple calculation. Anybody can tell you that, okay, it's similar to adding 1 to 10 lakhs. So automatically the new number will be close to 10 lakhs only, not 1. Similarly here, the 10 crore will be prevalent. So in the extrinsic semiconductor, okay, you can simply say there are 10 power 17 holes. Why? Because when you add 10 power 17 and 10 power 11, okay, already 10 power 11 holes were present. You have made another 10 power 17. So automatically the new number prevails. So accordingly, it's a common sense to say that the number of holes in the final block will be 10 to the power of 17. You can say almost equal, or you can say equal. There is nothing wrong in that. Okay. Now, similarly, when you add a 5th group element as impurity, the number of electrons, okay, in the final extrinsic semiconductor will be equal to the number of impurities that you have added. Okay. So in the extrinsic semiconductor, the number of carriers of that type, based on which impurity you add, they directly depend on the number of impurities. Okay. The other carrier, how to find, we have to discuss. So there are 2 types of carriers, holes and electrons. If you add 3rd group element as impurity, the number of holes is directly equal to the number of impurities. Or if you add 5th group elements, okay, as impurity, the number of electrons is equal to number of impurities. That is, clear. Now, how to find the number of electrons? So basically, here we need to discuss a little more. If you see, to 10 power 11 holes and electrons, we have added 10 power 17 holes. So the hole density has become much, much larger than the electron density. So electron, as it goes earlier, okay, it was a one-on-one correspondence. Okay, so there was some electron, there is some hole. So the electron comes, and if it can again drops into hole and de-excites, maybe somewhere else a hole electron pair is formed, so the equilibrium is maintained. However, now what happens is that you have too many holes, very less electrons. So wherever the electrons go, they do find a hole. So they may have more chance of getting de-excited. Okay, and indeed that happens because of the equilibrium. Earlier, a number of holes and electrons were equal. Number of holes have become too many. So automatically, okay, the electrons will try to kill those holes, but they fail because their number is very less. However, in that process, the number of electrons reduced drastically. The number of electrons drastically get reduced. Okay, and how much they get reduced when the equilibrium will be achieved? All this is answered in the NCERT textbook as that while in the intrinsic semiconductor, if you multiply the number of electrons and number of holes, you will get Ni square because both are equal to Ni. That rule shall be satisfied even in the extrinsic semiconductor. So we have a rule. The rule says that whether it is intrinsic or extrinsic, any semiconductor, the number of electrons and number of holes when multiplied, that shall always be equal to Ni square, where Ni is number of intrinsic carriers in the original semiconductor. Okay, so in this case, the final number of electrons, let it be Ne. Number of holes we know, which is equal to number of impurities, that is 10 power 17. When I square the Ni square, I will get 10 power 22, as you know. The simple calculation reveals us that number of electrons are now 10 power 5 per unit volume. So if you see, we had 10 power 11 holes and 10 power 11 electrons in the original intrinsic semiconductor. But when we make the number of holes to be 10 power 17 by adding impurities, the number of electrons drastically reduced to 10 power 5, so that the multiplication always remains the same. Okay. So to tell you, when you are discussing about the p-type extrinsic semiconductor, the key points to remember are an intrinsic semiconductor. If you take and if you add a third group element as impurity, you form a p-type semiconductor. P-type semiconductor has holes as majority carriers. Because of the majority of the holes, automatically the electrons become minority, and the electron density and hole density, their multiple, will be same as that of the intrinsic semiconductor, and therefore as the number of holes increase drastically, number of electrons also decrease drastically. Okay, so in a p-type semiconductor, holes are majority carriers. Holes are called majority carriers. And electrons are minority carriers. Okay, so these are important things. Okay, you should remember that the number of holes and electrons, the multiple, okay, of number of holes and electrons will remain same, okay, in the intrinsic as well as extrinsic semiconductor. Okay, and in a p-type semiconductor, holes are majority carriers, electrons are minority carriers. In an n-type semiconductor, electrons are majority carriers and holes are minority carriers. These are some very important points that you must remember, okay, when it comes to extrinsic semiconductor. Thank you.